And it's all you, John.
Is it 3 o'clock right now? I don't have my
It's 2:59.
Okay, hold on a minute.
2:59 and 54 seconds, so it's pretty close to 3.
Okay. For some reason, my computer time is always in Greenwich Mean Time.
That's kind of weird.
The reason is because I have a dual boot Linux system, and every time I switch from one to the other, it messes up with my time.
That's strange.
And I don't know how to fix it, but in any case.
Sounds like a classic Linux problem of like, I should be able to fix this, but I really don't know how.
Yeah, exactly. That's what it is. Let me get
All
my
right,
camera on.
I'll shut up. I'll mute myself.
Okay, so we'll get started here. One thing I wanted to make an announcement about first is I have a scheduled office hour. I actually have 2 today at 5:30 and 6:30, if I am remembering this correctly. So as always, the scheduled office hours are free and open to anybody who wants to come in. Each student for these hours are scheduled for 1 hour. However, if they finish the questions early, which I suspect that they will, or at least one of them will, then I open the floor to anybody else who might have questions. I do know that a lot of you have been emailing me about various debugging issues. So if you have a chance to stop by, I'm probably going to run it up until about 7:30, maybe 8 o'clock, just depending on sort of how many people I can respond to. But yeah, if you have time to stop by and you need a question answered, hopefully you can get your question in. There is sort of like a sort of waiting list in a sense, because like I said, I have probably half a dozen people who emailed me who needed debugging issues fixed or addressed, but we'll see how many we can get through. Okay.
Can I hop in real quick, John?
I'm sorry. Yeah, go ahead.
So if everybody could take a look over in chat, I'm going to post a link to a form there. That's a form that's going out for all undergraduate engineering students in JSOE. If you have some time to fill that out, it's more of a how are you doing right now form. It does look like we're going to be staring at COVID for the next few quarters. And so we're trying to get feedback from our students to find out where are some areas that we in general can improve, and also just to know how you're doing, so that if we can try to locate some more resources that would help students, that we can make them available. So it's an anonymous form. It's entirely optional. It will be shared with everyone in JSOE. So it's not just this class that's doing it or this department. Everybody in JSOE is filling out that form. So if you have time, fill it out, but please don't feel pressured to do it. It is entirely optional.
Just a sort of follow-up question here, Dr. Drews. Has it been finalized that we're still doing remote schooling in fall? Because last I heard they were potentially opening up in fall.
It's going to be a mix in fall, most likely. It is not set in stone what we are doing one way or the other, at least not that they've told us. Right now, the general understanding among faculty members is if the class can be taught remotely, they're going to ask us to teach it remotely. If there are other courses that are better done in person, then we'll try to figure out how we can do that and still follow the states and the federal guidelines for things like social distancing.
Okay, all right. Good to
But
know.
yes, you're right. It is not set in stone, so it is up in the air. But the kind of general idea of that survey is if we can plan for it to be remote, then we'll have some time that will allow us to do better.
Okay, good to know. So fill out the survey if you have a chance, or if you feel like it. The survey is in chat. Okay. So to sort of follow up with what Dr. Drews was talking about last Wednesday, today we're going to be doing examples using PBRs. I have 2 examples lined up, and I hope that we have time for both of them. There's going to be, so I'm going to work out both problems by hand and also in MATLAB. So these problems will be capable of being done by hand. But you know, if we don't have time to review the MATLAB for each one as well, then I'll be posting both of them online. So just a quick review. We're going to need to know 2 main equations here, which is the material balance for the PBR, which is written in the form dNi dW is equal to Ri prime, Ri prime, and then where our initial condition is at weight of catalyst equal to 0, where we have Ni naught, our inlet flow rate for the species. And then our energy balance, we're actually not going to use it today. So these examples I have lined up are going to be used purely for into line with the material balances. But if you wanted to recall, the energy balance is dTW del Q prime minus the summation Rj delta Hj over the summation Ni CPI. So both of these should look fairly familiar to you because as previously mentioned, they're very similar, if not almost identical to that used in PFRs with maybe the exception of the units on some of these terms. So the initial condition for the energy balance is, of course, that the inlet temperature is T naught. Yes, there is a prime. Thank you. Here's another important thing to that's just generally useful to remember is the units of R prime, which in this case is going to be it's defined as the amount of I reacted per unit of catalyst weight per unit time. And it's defined as Ri divided by rho bed. Okay, so with that out of the way, we can jump into this example here. And so our example is given the reaction, the gas phase reaction, A plus B goes to C. Is an elementary or follows an elementary rate law. And that K at 400 K is equal to 0.1. The units on this are going to be liters squared per mole seconds, and then kilogram of the catalyst. Nu naught, or excuse me, V naught. Caught myself this time. V naught, not volumetric flow rate, not nu as in the stoichiometric coefficient, is equal to 4 liters per second. A and B are fed at equimolar ratios. Equimolar ratios. So the units for K at 400 K is liters squared per mole seconds, and then this is kilograms of catalyst. A and B are fed at equimolar ratios at 400 K and 5 ATM. Find the mass of catalyst needed for 70% conversion. Okay, Okay, so this one is a fairly straightforward problem. Like I said, the problems we're going to be doing today can be done by hand. And so this one only requires the material balance. So we're going to start with that. The material balance, of course, is dni dw is equal to ri prime. And we're going to be doing the balance on A in this case. So we can write dna dw is equal to ra prime. And because it's an elementary rate law, we know that ra prime is equal to negative k ca cb. Do we have na naught? That's a good question. I don't have it in my notes, so I'm going to say no. I don't think we need it. No, we don't. Well, we're going to solve for it, actually. And so we know that the rate law, like I said, is RA is negative K CACB. And so just doing a quick rearrangement here and plugging that in, we can get dna dw is equal to negative K CACB. Because we know that based on stoichiometry and the fact that these are, this is an equimolar feed, we know that A and B are consumed at the same rate. And so no, so to the question chat, there's a question, is row bed missing? As far as I'm aware, no. No, we shouldn't need it. And so because of the stoichiometry of the reaction and that we're given a equimolar feed, we can say that A and B are consumed at the same rate. So we know that CA is equal to CB. This is, oh, good point. I didn't specify that. This is isothermal isobaric. Thank you. Okay. So continuing, we know that CA is equal to CB. And then this would mean that we could substitute this as negative K CA squared divided by dW. And I think from here, the solution is similar to a previous example I did, maybe, it might have been 2 weeks ago for a PFR example, but we're going to make a substitution for CA, where CA is equal to NA over nu naught. And this gives us that, here we get negative NA squared over nu naught squared, negative K, DNA on the left, dW. And so this becomes a relatively simple matter of separation of variables. And so moving this over, we get DNA over NA squared is equal to negative K over V naught, not nu naught, that's a V. V naught squared. This is gas phase. Yeah, gas phase. Okay, so I'm getting a couple questions here. So one is that the why isn't would it be V instead of V naught then? So because it's isothermal and isobaric, V is equal to V naught. And because the If I'm not mistaken, V should be equal to V naught actually. Actually, I think, yeah, so to the people in chat, they're all pointing out more or less the same thing, that in this case, I believe you guys are correct that V is not equal to V naught, because the moles are not conserved. And the reason is because I wrote the equation wrong. There should be a 2 in front of the C. That should fix that issue, because then we get, from the ideal gas law, we know that PV is equal to NT RT. And then from there, if we were to divide it by P naught, V naught, NT naught, R, and T naught, because it's isothermal, isobaric, V over V naught is equal to 1. So sorry about the confusion there. Okay. So from there, we know that V, and so I'll write this out explicitly, V naught is equal to V. This is by the stoichiometry and ideal gas law. Yeah, that makes sense now. Sorry about that. I'm trying to check this as we go here, because so many people were pointing out my my mistakes. Okay, so from here, we've seen this differential equation before. This will come out to be -1 over NA minus, when we integrate over NA naught to NA. There's a dW over here on the right, and integrate from 0 to W. We should get -1 over NA plus, I think, plus 1 over NA naught is equal to -K over V naught squared dW. And then using some of the information that we were given, we know that YA naught is equal to 0.5. That's from the equimolar feed. And then knowing that P was equal to 5 atmosphere, and the fact that this is the gas means that we can define the concentration CA naught as equal to YA naught P over RT. And if we were to plug those values in, here R is equal to, I think it's 0.82. Somebody can check the units on that, but this is the atmosphere units of R, I believe. And this, calculating that, gives us a CA naught value of 0.076. 0.076. And then from there, we can calculate NA naught as CA naught V naught, which should come out to about 0.304. This is in moles per second. Isn't there a question was, isn't there a W in the denominator of R? No, there shouldn't be. If there was, then this becomes a non-separable equation, if I'm not mistaken. In this case, it should be separable. Okay. From there, we continue to just plug in the values that we have. So here we know that NA, we can do a substitution for NA, which is NA naught times 1 minus XA. XA was given as 0.7, so making that substitution and moving this negative to the other side as well. We're going to get that we have 1 over NA, NA naught times 1 minus XA, minus 1 over NA naught times V naught squared over K is equal to W. And then from there, W is equal to, you can do the calculation, plug in the numbers that we have. So we know our NA naught, we know XA, we know NA naught again, we know our V naught, and we're given K. So from that, we can calculate that W is equal to 1,228 kilograms of catalyst. So a fairly high amount of catalyst. So question, yes, there, okay, so I think a couple of people are asking this question about the density of the bed. So the R value that I used here is, oh, I see the confusion. I specified that RA prime is equal to negative K CA CB. Now, the confusion with the row bed that a couple of people were asking about was that the definition of RA prime is equal to RA to keep the species consistent, RA divided by row bed. However, here I specifically mentioned that RA prime is just equal to this rate law. So you can assume that the density of the bed is built into the rate law. Now that's, in fairness, that's not typical, but essentially what this would be if, because I didn't give it to you, my camera's out of focus. Because I didn't give it to you, you wouldn't be able to calculate this if there was a row bed in the denominator there. But what that, if you were given it, all it would be is a constant that's in front of the R term. And yes, that's because K is given in the correct units. So the units of K here should account for the sort of the missing density. So a question was, can I explain how CA is equal to CB? So that comes about from the stoichiometry and the equimolar feed. So because the stoichiometry is a 2 for 2 and the equimolar, the A and B are input at an equimolar ratios, meaning half A, half B. We know that they're consumed at equal rates, so CA is equal to CB. One thing about that actually that is important to point out, if you were to say that CA and CB were not equal to each other, you would come out with a different differential equation, and your answer would be completely wrong, because since we have to write the expression in terms of NA, moles of A, that includes assuming that CB is a function of NA, which means we have to, again, we have to take that into account when we're doing the differentiation. So if you don't take that into account during the differentiation, your integral will come out different down here, and so you'd get a completely different answer. So there is, I have a MATLAB code that solves this whole thing, but it's almost, well, it's almost 10:30 in England, which I assume is going to be 3:30 here. So I won't go over the MATLAB code right now, but here's the plot of the MATLAB code. And so we can see that there's probably some rounding issues here, but we're about right. So at 70% conversion, this is XA is equal to 70. We get roughly 1,200, about 1,200 kilograms of catalyst. This is W on, I should have labeled this, but this is W on the X and XA on the Y. So I'll be posting the code that you can look over alongside the handwritten notes later today. Okay, so that was the first example. That was a little bit rougher than I thought it would be, but that was my own fault. So continuing, our next example is actually quite a bit more complicated. At least it looks a lot more complicated. That's not necessarily the case once we start going through it though. So we're given a gas phase reaction again. And in this case, it's two reactions. So it's 2A goes to B plus C, and then B plus D goes to E plus F. So we have multiple reactions. Now this one might seem overly complex, but it actually can be done by hand relatively simply because of the sort of information it's given. It's helps us out quite a bit. So given that these reactions occur in a isothermal and isobaric PBR, K1 is equal to 12. The units on that are meters cubed squared divided by moles, moles, seconds, kilograms catalyst. R1 is equal to, sorry, to be more specific, R1 prime, KCA squared. And then R2 prime is equal to K2CD. Notice here that the second reaction is first order in species D, has no dependency on CB. And we'll make use of that little thing, that little note for the second part of this problem. And then we're given that K2 is equal to 0.074 meters cubed per second kilograms catalyst. The feed to the reactor is provided in a ratio of 75 to 25, A to D. So this one is not equimolar. And it's fed at 1 ATM and 400 K with the volumetric flow rate V naught is equal to 10 meters cubed per second. So part A here, oops. Part A, find the concentration of A. Given W is equal to 50 kilograms of catalyst. Okay, so again, as always, we start with the material balance. So DNA dW is equal to RA prime. And this is going to be equal to negative K, K1, CA squared. So just like we did before, we know that we're going to have to, when we do this differentiation, or sorry, when we do the integral, we're going to integrate this DNA between NA naught and NA. And we're not given an NA naught. So what we're going to do is basically we're going to solve for it first. So I'm going to write out essentially the same equation that we had before, which is CA naught is equal to YA times P divided by RT. And so because we're given a ratio for the feed, we know that YA naught is going to be 0.75, P is going to be 1, and then R and T are going to be 0.082 and 400K respectively. Doing this calculation and then also solving for NA naught as CA naught times V naught will give us 0.228 moles per second. So continuing with our differential equation here, we can do a substitution for CA. And so CA is going to give us that CA is NA squared over V squared. Now, in this case, similar to before, we are given that, given this set of reactions, we know that it's 2A gives me 2 moles or 1 mole of B and 1 mole of C. So delta for this equation is equal to 0. And delta for this equation is also equal to 0. And so because of that, we are going to know that just like in the previous problem, in spite of it being gas phase, V is equal to V naught. And the fact that it's isothermal and isobaric. And so making this substitution, we can then say that this is equal to K1 NA squared over V naught squared. DNA dW. Now from there, we more or less follow the same sort of calculation steps that we did before. So by separation of variables, we get DNA over NA squared is equal to negative K1 over V naught squared dW. And doing, this is, if I'm not mistaken, this is exactly the same integral here. It's a very common integral you'll see in a lot of different problems, but here you get NA plus NA naught is equal to negative K1 over V naught squared. So we integrated this from NA naught to NA, and we're integrating this from 0 to W. So we get just W on the right side. From there, we're going to be solving, the difference between the two problems now is we're solving for CA instead of before we solve for the weight of the catalyst. So just by some rearrangement, we know that, again, I'll write it on the side, CA is equal to NA over V naught in this case. And so making that substitution, we get V naught over CA plus V naught over CA naught. And then we can multiply this whole thing by negative V naught squared over K is equal to W. And actually, based on, I think I might have made an sort of unnecessary algebraic simplification there, but once you rearrange this whole expression, it's not too bad. It's a little bit messy, but once you get the, once you rearrange it, you can solve that CA is equal to 0.0097 moles per meter cubed. So we get that from knowing that V naught was given, CA naught we calculated. Again, this is given, this K value is given. This, by the way, was K1 to be more specific. And then W was given as 50. So one equation, one variable, rearrange and solve. Now, part B, I think is the sort of more interesting part of this problem. Part B is find CB, find the concentration of B. Now, I'm going to rewrite the equations here because we're going to sort of determine how to find CB, or the easiest way to find CB, sort of by inspection of the equations. And so we know that the equations are 2a goes to b plus c, and b plus d goes to e plus f. Now, if I were to write a material balance on CB, that's probably the first thing you're thinking of in order to determine what concentration of B is. We could write our material balance on B as dNB over dW is equal to RB. And here RB is going to be equal to basically R1 minus R2, so the generation minus the consumption. And notice though that when we do the substitution for what those R values are going to be equal to, and these are all R primes, by the way, when we make that substitution for what the R values are equal to, we're going to get that R1 is K1 CA squared minus K2 CD, K2 CD. Notice that there is no concentration of B in this case. Like I said earlier, the rate of reaction 2 is not in any way dependent on the concentration of B. And just the fact that this rate law is sort of more complicated than we would like it to be, because it's the difference of two different rate laws. In order to solve this particular material balance, we're going to need to solve the material balance on D. And so what we could do instead is by inspecting these equations, we can notice that, okay, if we want the concentration of B, which shows up in two places in the two reactions, rather than solve this sort of more complex material balance, if we just instead solve the material balance for D, which shows up in only one place in reaction 2, then we could use stoichiometry to determine what B is. And so instead of doing a material balance on B, we're going to instead do a material balance on D in order to determine CB. That's meant to be B, CB. Another way to look at this, like I said, is do the easy material balances first. And when I say easy, I just mean for the species that show up in only one reaction. That's sort of a good general strategy to use if you're doing these by hand, at least. If you're doing this in MATLAB code, which if we have time, I can show you at the end, you're basically going to use all the material balances anyways. So the material balance on D is going to be dND dW is equal to RD. And going from here, because we're going to be solving for concentration, I'm going to actually be making a substitution here that might make our math a little bit easier. And in fact, it makes the algebra a little bit easier. And the substitution is simply that ND is equal to CD times V naught. So doing that substitution, we get that V naught D CD dW is equal to RD. And in this case, we can write RD is equal to negative K2 CD. Okay. From there, this differential equation is a little bit different because there's no square term on our variable here. And so rearranging this, we can get dCD divided by CD is equal to negative K2 over V naught dW. And then integrating this and this, we go from CD, oops. We're gonna go from CD naught to CD and from 0 to W. And then rearranging, or not, sorry, not rearranging, solving the integral, and then rearranging for CD. You can work it out. These are still prime, right? Yes, sorry. This is a RD prime and RD prime. But RD prime was essentially given as R2 prime in the problem statement. And so rearranging this, we can determine that CD is equal to 0.0053 moles per meter cubed. So like I said, this integral is slightly different. The only thing you'd have to do is, I think, off the top of my head, I think it's like a ln, the integral of 1 over x is ln x, and then rearrange and solve from there. But you should come out, the reason for this substitution for substituting ND for CD is simply because we're solving CD, so we can get our answer with directly with a little bit less algebra. Oh, the other thing here that I forgot to mention is CD naught. You might be wondering, where did we get the value for CD naught in order to do this calculation? CD naught was given, not given directly, but it was presumed from the given information. Since we know that there's a 75 to 25 ratio of A to D, we know that the concentration, the inlet concentration of CD is simply 1/3 of the inlet concentration of CA naught. And CA naught we solved in the previous problem. So if I recall correctly, CA naught was 0.023 about. And so, so that means that CD naught is comes out of that expression. Question, do I mean 1/4? No, I mean 1/3 because the ratio is 75 to 25. So you have 3 times as much A as you do D. Okay. And so we have about 8 minutes left. I'm gonna put the code up here so we can take a look at it. I don't think we have that much time to really go into too much detail about it, but actually, instead of doing that, I'll show you what the plot looks like for these 2 species. So this is the plot that you would get out of the code that I'm gonna post up on MATLAB. I'm sorry, on Canvas. But this one here is our concentration of A, and this one here is our concentration of D. And so in this, oh, sorry, you're right. It did ask for CB. I did not finish this problem. You were correct. So to find B, it's only a few steps from here. So because now we have the concentration of D, we can then say that NB is equal to, now again, this is going to come from stoichiometry. So if we look at our reactions one more time, 2A plus B plus C, 2A goes to B plus C, and then B plus D goes to E plus F. We know that from the stoichiometry, NB is equal to NA naught minus NA divided by 2 minus ND naught minus ND. And so what this is saying is that this expression here, NA naught minus NA, if you take the amount of A that got converted and then divided by 2 because of the relative stoichiometric coefficients between A and B, you can get the moles of A generated from reaction 1. And then we have to subtract the moles of B. So this is reaction 2, reaction 1. We have to subtract the moles of B that are consumed by reaction 2. And so all of these values are known. So we know that's, and I'll write it off to the side here. We know that CA naught is equal to 0.023, CA is equal to 0.0097, CD naught is equal to 0.0077, and CD is equal to 0.0053. And we can then rearrange this expression to be in terms of concentrations. So we get V naught CA naught minus CA divided by 2 minus V naught CD naught minus CD. And then from there, we can get that NB is equal to 0.043. Okay. And so in terms of the MATLAB code, I actually saved the plot for the wrong data because you are correct. I should have solved for B, but when I was doing the MATLAB, I only solved for D. But it is I'll adjust the code to plot for CB as well. And so you'll be able to see that in the code that I'm going to upload. So this, strictly speaking, this was CA, and then this was CD. And I will adjust the plot to also plot for CB. Okay, so we only have a few minutes left here, so I think I'll just end it here. I'll post both of the codes. N.043 is CB. It should be CB. I just, all I did was, so in this case, this is NB on the left side of the equation. I made a substitution on the right side for the various concentrations. So yeah, in order to determine CB, then it would be NB divided by V naught. V naught was 10, so CB is just 0.0043. Thank you. Yeah, no, sorry, okay. Yeah, sometimes when I'm writing these questions, I forget to answer them. It happens sometimes. So yeah, what was I saying? I'll adjust the code and post the corrected one on MATLAB to also plot CB. But as always, I will hang around for a few minutes to answer any questions. The axis for the second plot, when I post up the code, I'll make sure to add the labels. But this is just concentration of species I, and then the bottom down here is the weight of catalyst. So question for problem 2 of homework 5, my y-axis goes from 0.998 to 1, while the solution goes from 0.999 to 1. Yeah, that could just be a rounding error. I mean, if the shape of your graph looks generally correct, I wouldn't worry too much about it. You might want to check that because you're on the right scale, it's not likely to be a unit issue. It could be something wrong in your constants or inputs though, but you're off by 0.001. It might just be the way that it's plotted rather than the actual values of your pressure drop. So I wouldn't be too concerned about it. For homework 5, problem 3, how do we know what the CP value is? You can look up the CP values. You can look at the CP values in the back of your book in Appendix D. It was 998. Yeah. So it didn't seem to be an issue of scaling. Why do the plots in the pressure drop in part 2 have cutoffs? I think you might be looking at the redacted graphs. In which case you want to check out the updated the updates on the homework problem. They should the lines on the updated graph should go all the way from beginning to end of the reactor. Oh, okay, never mind then. So the that's just the intention of the plot. Do we choose the CP value with the one with the closest to T naught? I'm not 100% sure. Could you restate your question? Yeah, the redacted graphs are intended to, I guess, hide the entire solution from you. Your graph should not stop short of the full reactor volume. I don't think it should, at least. Yeah, no problem. Since CP values are different for different temperatures, which one do we choose? In this class, if I'm not mistaken, CP values are considered constant with temperature. So you do have to make adjustments, I believe, to your del H, which is includes CP times delta T. So your delta H will change because you're going to be using the reference delta H of formation in the back of the book, in addition to the CP values, which we assume to be constant. For 5.2, what happens if our line goes down as far as 0.999? Then that's just implying that there's not a significant pressure drop across your reactor, which is fine. Again, so the graphs that you're probably seeing on the homework are redacted intentionally. So you'll only see part of the graph. The rest of it presumably, goes in the same general trend. Just gonna play some music while we're waiting for any last minute questions here. this one definitely should not be flagged by YouTube. It's just Beethoven, so. I guess we can end things here. Just a reminder, if anyone's interested, my office hours today between 5:30 and probably about 7:30 for individuals who are scheduled. So if you wanted to maybe get your questions answered, hopefully, then you can hop in. But there's no promises because that time is scheduled for the students who schedule that time with me. Yeah, I do, Dr.